off now, still of course much higher than people would like to see, but at least we're not seeing that upswing continue. As has been true since the beginning of the pandemic, the GBT remains in full operation, and all of our work is continuing with the GBT and its instrumentation. It's a little bit slower, a little bit more complicated to get things done in a safe manner, but it is happening. But of course, the one thing that isn't going on site is a lot of our education programs. All the on-site visitor programs remain canceled, including the Science Center. We do, of course, have some fantastic virtual and remote educational activities taking place, and lots of credit to the education and public outreach team for finding ways to do that. But unfortunately, a lot of the activities remain canceled. Big news with the GBT right now is the new LASSI system. That is the laser scanning system that scans the surface of the dish in real time and then provides feedback and corrections to the dish. Is almost ready to go up onto the telescope. So this is going to be a fantastic instrument once it's fully commissioned and up and running. It's going to provide a better surface accuracy for the high frequency observing, and also open up many hours on the GBT for high frequency observing. We have the full weather housing complete. So this is a big protective weather housing, big system that opens up wide, let it view the telescope. All of that's done. It's deployed in the lab at the moment with full hardware and software testing has been taking place in the lab, and everything's working great. So the plan is to put that up onto the GBT next week and begin the commissioning of the actual system in earnest. So that's really exciting news for us, and in a month or two, we should have some great results coming out of that. Other news going on with the observatory, just to let everybody know, we have an Argus 144 workshop coming up at near the end of September. The abstract deadline for that is passed, but of course registration is still open on that, so feel free to go take a look. If you just go to the main GravemacObservatory.org page, you'll see a link over to the Argus 144 workshop. Also this fall, we have an observer training workshop on October 13th and 14th. This is a great chance to either learn how to use the GBT if you've got experience in radio astronomy but not experience with our telescope, or if you just want a refresher course, if you haven't used the telescope in a while and you want a chance to remind yourself, the best practices in using our telescope, that registration is also open. And again, you can find the link on our primary webpage. So with that, again, let me just thank you guys all for joining this. And I'm going to stop sharing my screen and I'll hand this off to Toney Minter. And if anybody has any questions for me, feel free to post them within the chat or the Q&A system, or anytime during any of this talk. And hopefully Tony's got the screen, so I will stop talking now. Thank you. We've got your screen, but no voice, Tony. I would tell great jokes and do other great impersonations, but I have none as Tony gets the technical sides sorted. There we go. Now you're good.
All right, just want to remind people that the proposal deadline is coming up next Monday. It'll be 5 p.m. Eastern or 20 hours UT. Also want to remind people of the Observer Training School, which Karen just mentioned. We have planned on having the Single Dish Summer School this past May. That got canceled, obviously. Plans are in the works to have that happen late spring of next year. And just be on the lookout for details as we're still working out those plans at the moment. That's everything that I have, so we can go on to the next presentation.
All right, so now our main event here, we have Thankful Cromartie giving a talk about some of the Shapiro delay work that she's been doing. And hopefully we'll be able to switch over to her screen in just a moment. Okay. There we go. So thankfully you ought to be able to take over on the screen there.
Alrighty. How does this look?
Fantastic. Great.
Awesome. Okay. Well, thank you all so much for having me. I'd like to talk to you today about two recent relativistic Shapiro delay measurements we've been able to achieve with the GBT of two pretty interesting millisecond pulsars. Some of this won't be news to you, and maybe some of it will be. Oops. Okay, we're going to speed through basics. Millisecond pulsars are a subset of the pulsar population that's been extremely rapidly. They're very old and most of the time in binaries. They have relatively weak magnetic fields, and we know of just over 300 of them, while we know of 3,000 regular pulsars. So the reason why millisecond pulsars are such powerful tools is because they're great for pulsar timing. They spin down extremely slowly, and so they're kind of space-based clocks. We call pulsar timing this technique where you're accounting for every single pulse from a pulsar over very long periods of time. And so if you create a model where you know when every single pulse is going to arrive, then you know that if there's a difference between the pulse arrival time that you actually measure and the predicted time of arrival, then there's some external effect intervening, something like the interstellar medium, GR effects, all kinds of interesting things. And we call those deviations timing residuals, differences between the measurement and our model. So on the bottom is an example of what a good timing model might yield. The residuals are really nicely scattered around 0. And then on the bottom panel is what happens when your model is missing a parameter, such as proper motion. You can see that deviation grows over time. So all of this work is being conducted in the context of the NANOGrav, North American Nanohertz Observatory for Gravitational Waves collaboration. And NANOGrav is obviously a project that's extremely reliant on the GBT. The goal of our project is to detect a stochastic background of gravitational waves that's low frequency, coming from supermassive black hole mergers all over the universe. And so our project consists of monthly dual frequency observations of now more than 75 millisecond pulsars. And we've been, we're working on our 15-year data set now. So we've been doing this for a while. Our data set's extremely rich. And that rich data set is great for, so-called secondary science projects, things like, solar wind modeling, general relativistic tests, cosmic strings, all kinds of interesting things. But the one that I am excited about are neutron star mass measurements. So we'll start out by talking about the very massive millisecond pulsar J0740 plus 6620. The reason why these mass measurements are so important is because they help us constrain the neutron star equation of state, that describes the way extremely dense supernuclear density matter behaves deep down in the cores of these neutron stars. And one very convenient feature is that these equation of state models are translatable into physical parameters, observables. So you can see the mass radius diagram on the right. By measuring more and more massive neutron stars, we can rule out more and more equations of state, because each equation of state must account for a pulsar with a mass that high. And so the question is, how do we measure these neutron star masses very precisely? And one of the ways to do this, there are other ways, but one of the really great ways to do this is using relativistic Shapiro delay. So normal pulsar timing gives us 5 Keplerian parameters for binaries, things like binary orbital period, eccentricity, other things. Shapiro delay is an effect that occurs at superior conjunction in the orbit when the pulsar passes behind its binary companion, which is often a white dwarf. When it's behind its companion at superior conjunction, the companion is deforming space-time in a way that slows down the arrival time of these pulses. And we can parameterize that delay in the timing, in the times of arrival, with 2 parameters called range and shape. So these 2 post-Keplerian parameters can be directly measured and then combined with the mass function in order to yield independent measurements of the pulsar mass and its companion's mass. And so that's a really powerful tool to have at our disposal. So here's kind of a toy model of the Shapiro delay residuals. So we mark orbital conjunction, or superior conjunction is happening at orbital phase of 0.25. And you can see that's when the very large spike in timing residuals occurs. You can also see through the different colors of different shades of blue that Shapiro delay is very strongly dependent on inclination angle. And so that basically means that we can't measure this effect all that often. The binaries that we're looking at have to be very edge on in order to make a good measurement. So a quick history of neutron star mass measurements. The first kind of 2 solar mass neutron star that broke the canonical idea of, neutron stars are 1.4 solar masses was from Demarest et al. In 2010. We now know that millisecond pulsar has a mass of about 1.93 solar masses. And that measurement was obtained through Shapiro delay. That source is a NANOGrav pulsar as well. The second was in Toney et al. In 2013 with a more than 2 solar mass neutron star. That mass measurement was obtained through white dwarf radial velocity observations as well as pulsar timing. And then more recently, the LIGO double neutron star merger is also able to put an upper limit on what we would expect for neutron star masses. And that value is something like 2.17 solar masses. So JO740 plus 6620 was found in the Green Bank North Celestial Cap survey in about 2014. And since then, it's been part of the NANOGrav pulsar timing array. It's a really great timer. It's a high quality source. And so after 4-ish years of timing as part of the NANOGrav array, we started to see a hint of Shapiro delay. And that led us to include that source in a project where we were looking at 4 different sources over superior conjunction to see if we could get good Shapiro delay measurements for them using the GBT. And so for this source specifically, we were able to see Shapiro delay and refine our measurement quite a bit. And it yielded a 2.18 plus or minus 0.15 solar mass measurement when, in combination with the NANOGrav data that we had. And so that's a number that's very intriguing. It's extremely high. It would be very exciting to see a pulsar that massive, but it's not really anything that you can report because the error bars are just too large. And so that motivated us to perform some simulations and apply for DDT time with the GBT. We got 10 hours over superior conjunction and in one of the Shapiro delay troughs. So you can see in the figure on the left, the green is kind of the nominal Shapiro delay curve. And then the black shows a simulation where we were basically just trying to figure out the best observing scheme. So you might think that logically the best thing to do is to try to measure the full extent of the Shapiro delay curve, and that turns out to be right. So you want an observation or maybe a couple observations over superior conjunction, as well as observations in the Shapiro delay troughs. And so that's what we were able, we were able to get, and combining that, those targeted observations and the targeted observation from before with all of our NANOGrav data, this all taken together yields a mass measurement of 2.14 plus or minus 0.09 solar masses, which was extremely exciting. So this is the most massive neutron star known to date. And we reported our results in Cromartie et al. 2019. On the right, you can see these three panels show basically the full model, including Shapiro delay parameters. The second panel is what we're actually sensitive to. So what happens when you don't know the inclination angle and companion mass a priori. And then the third panel is the full extent of the Shapiro delay signal. So what does this mean? Higher mass neutron stars require stiffer equations of state. And this means that this kind of measurement is in tension with non-nucleonic proposals for equations of state like quark matter, hyperons, Bose-Einstein condensates, things like that. And you can see the importance by looking at the plot on the right for us to get some more precise some more precision on that mass measurement, because there's still some I don't know, improvement would be great. So that's what we're trying to do. We now have, because it continues to be observed with NANOGrav, and we're including it in every observing session we have with the GBT. And we're also getting observations with the CHIME telescope approximately daily, which has also been very important. This source is of interest to the NICER X-ray team. They are going to use updated mass and parallax and so forth measurements to inform their light curve modeling for the source. And so right now, combining CHIME data with all of our NANOGrav data, our targeted observations from the GBT, we are measuring the mass to be about 2.13 plus or minus 0.07 solar masses. So I won't go into too much detail because these results are going to be reported in a couple of different forthcoming papers. But the takeaway is basically that this is very much in line with our expectations. And so this is a sort of a nice result. So secondly, I'll talk about J1231 minus 1411. This is another millisecond pulsar discovered with the GBT. It's one of 4 targets of interest to the NICER X-ray mission, and it's also actually the brightest millisecond pulsar known in gamma rays. The X-ray light curves show a single dominant peak, suggesting that this source might be a little bit less massive. And the idea here is kind of similar to what we're doing with J0740. We want to combine radio Shapiro delay measurements with NICER's mass over radius constraint in order to better constrain the equation of state. And so we were able to obtain 22 additional hours of observations in addition to some observations that were taken with the Nancy radio telescope and some early observations with the GBT. So these 22 additional hours in targeted observations included 2 conjunction phase observations, which was very helpful. And so we've been working on combining those recent observations that were taken in spring 2019 with the archival Nancy and GBT data. So we're looking at these data in a couple different ways. Just by doing kind of a chi-square grid using normal pulsar timing techniques, we get a mass of about, it's not a great mass constraint, but it does suggest that the mass is low. So 0.75 plus 0.55 minus 0.3-ish solar masses. So not a good constraint, but certainly, verifying our idea that this is a low mass source at a very high inclination angle. But we're also using a different technique. So Markov-Chain Monte Carlo modeling for pulsar timing is kind of just starting to come into vogue. And we wanted to make sure that we were using physically informed priors for these runs. So the first is on the companion mass. We wanted to use this well-known relationship between the mass of a white dwarf and the binary orbital period from Torres and Savonij in 1999. So this is the TS99 relationship. This suggests that the companion mass, given the well-measured orbital period, should be about 0.22 solar masses. And then on the inclination angle, we wanted to put a random distribution prior on. So that means it's flat in cosine of I. And so don't pay too much attention to these plots. We'll look at another one. This is basically just to show you, obviously you can't read this or anything. These are all the parameters we're fitting for and the kind of covariances and things between them. But it's not worth straining your eyes to look at. So here is an example. We ran 3 different MCMC trials with different priors on the companion mass. And this one is a very conservative example because it's a very flat prior in companion mass. And you can see that the data do actually inform our measurement of the companion mass, which is a very nice result. And they are very much in agreement with our original just chi-squared gridding, as well as the NICER light curves. So suggesting that this is a low mass millisecond pulsar. in a highly inclined orbit. So the one thing is that the companion mass is very low compared to what is predicted by TS99, which, you know, we're still thinking about. It's something to keep our eyes on for sure, but there are some new indications that this might be okay. There are a lot of other systems that are showing these kind of much lower companion mass measurements. So it's something to keep our eyes on. Oh, and the other thing to mention is, you know, it's not really a disappointment that this is a low mass millisecond pulsar. It's important to constrain, you know, both high and low mass millisecond pulsars are important for constraining the equation of state, especially as far as NICER is concerned. So it would be a mistake to be super disappointed by observations of a low mass MSP. They're extremely important as well. So we also looked at, independent of the GBT observations, we looked at the Fermi gamma ray timing over about 12 years of data. And so the takeaway is just that the data aren't very constraining, and we're not able to get a particularly meaningful mass measurement out of our out of those runs, unfortunately. But the radio data are hopefully going to be helpful for the NICER team in their quest to measure the mass over radius for this source. And that's about all I got. So thank you so much.
All right, thank you, Thankful. So we do have one question right now, and again, I encourage people to use either the chat or the Q&A if you have questions for Thankful. First question coming in is asking, are those X-ray counts at phase 0.5 and 1.5 real? And what do they mean physically? They don't seem to have a radio counterpart.
Oh, okay. I can't actually see the question. So you're talking about, oh, I also can't go back. Interesting.
Thankful you may have a Q&A button at the bottom of your screen.
I see. Okay. So you're talking about this plot, is that correct? I'm pressing the Q&A button and nothing is popping up. I'm not sure what that means.
Yes, they're talking about that plot. That's
okay.
Correct.
At
0.5, are those X-ray counts at phase 0.5 and 1.5 real, and what do they mean physically?
Yeah, there are others on the call who can answer that more definitively, but I think that is real. And it's all dependent, what you're getting from the X-ray light curve is totally dependent on the geometry of the hotspots and the mass of the source. And so the very high ratio of you know, peak to peak is physically something you can explain just with the geometry of the hotspots and the source's mass. So that is real.
And then the question, follow-up on that was also, does the X-ray then does not have any sort of radio counterpart? Is that correct? That those two emissions there?
I am not sure.
So if you look at your plot, the green X-ray where you've got the at a 0.5, 1.5 show the X-rays you just discussed.
Yeah, actually, I'm not the right person to answer this question because I'm not sure about the alignment of the radio and X-ray profiles. Maybe someone else on the call could answer that more intelligently than I could, but I'm not well versed in the you know, the alignment of these X-ray and radio profiles.
We'll have the usual awkward pause for a minute to make sure there aren't any follow-up questions in Zoom. And it looks like everything coming in right now is just thank yous to Thankful for the fantastic talk. So I will add to that, and thank you very much, Thankful, for this, and thank everybody else for their time, for taking time out this afternoon to come and listen. And keep an eye on your email. We should have more talks coming up. So Thankful, thank you again. Appreciate it.
Thanks so much for having me. Cheers, everyone.
Bye-bye.